In electrical systems, specifically open delta configurations, understanding the National Electrical Code, or NEC, requirements for conductor ampacity is crucial for safety and compliance. Article 310.15 (b4) within the NEC addresses situations where the neutral conductor's impact on ampacity needs careful consideration. The core principle hinges on whether the neutral conductor carries only the unbalanced load from other conductors or a significant portion of the total current. In an open delta system, the neutral conductor typically does not carry a substantial portion of the load current, especially if the system is balanced or primarily serving single-phase loads distributed relatively evenly across the phases. Consequently, if the neutral conductor exclusively handles the unbalanced load, Article 310.15 (b4) stipulates that this conductor is not required to be counted when determining the ampacity adjustment factors. The rationale behind this lies in the understanding that the heat generated by the current in the neutral conductor is minimal under balanced or near balanced conditions and doesn't significantly contribute to the overall heating of a conductors bundled together. In contrast, Table 310.15 (b2) comes into play when a neutral conductor carries a substantial portion of the load current, particularly in systems serving nonlinear loads. Nonlinear loads, such as those found in modern electronic devices like computers, LED lighting, and variable frequency drives, generate harmonic currents. These harmonic currents, especially the third harmonic and its multiples, can accumulate in the neutral conductor of a three-phase system. When harmonic currents are present, the neutral conductor can carry a current equal to or even exceeding the phase currents. This increased current flow results in significant heat generation, which impacts the ampacity of all conductors in the raceway or cable. In such scenarios, Table 310.15 (b2) mandates that the neutral conductor be counted as a current-carrying conductor, requiring adjustments to the ampacity of all conductors in the bundle. The decision of whether to apply Article 310.15 (b4) or Table 310.15 (b2) requires a careful evaluation of the system's loading characteristics. Firstly, assess the nature of the loads connected to the open delta system. If the loads are primarily linear, such as incandescent lighting or resistive heating, and are balanced across the phases, the neutral conductor will likely only carry a small unbalanced current. In this case, Article 310.15 (b4) applies, and the neutral conductor is not counted for ampacity adjustment. Secondly, consider the presence of nonlinear loads. If a significant portion of the load consists of electronic devices or other nonlinear loads, harmonic currents are likely present. Measure the current in the neutral conductor using a true root mean square, or RMS, ammeter to determine if it exceeds the phase currents. If the neutral current is substantial, Table 310.15 (b2) applies, and the neutral conductor must be counted. Thirdly, document your assessment. Maintain detailed records of the load calculations, measurements, and decisions made regarding ampacity adjustments. This documentation is crucial for demonstrating compliance with the NEC during inspections or audits. In practical terms, correctly applying these NEC guidelines ensures that the conductors in the open delta system are adequately sized to handle the expected current without overheating, thus reducing the risk of insulation failure, fire, and other electrical hazards. The ampacity of a conductor is defined as its current carrying capacity under specific conditions of use without exceeding its temperature rating. Several factors influence the ampacity of a conductor, including the conductor material, size, insulation type, ambient temperature, and the number of conductors bundled together. When multiple current-carrying conductors are bundled together in a raceway, cable, or enclosure, the heat generated by each conductor can raise the overall temperature within the enclosure, reducing the ability of the conductors to dissipate heat. As a result, the ampacity of each conductor must be derated to account for this increased ambient temperature. The NEC provides tables and formulas for calculating these derating factors based on the number of current-carrying conductors. Firstly, conductor material plays a vital role in ampacity. Copper conductors generally have higher ampacity ratings than aluminum conductors for the same size. This is because copper has a lower resistance to current flow, resulting in less heat generation. Secondly, conductor size impacts ampacity. Larger conductors have a greater surface area for heat dissipation and can therefore carry more current without overheating. The NEC provides tables that specify the ampacity of different conductor sizes based on their material and insulation type. Thirdly, insulation type influences ampacity. Different insulation materials have different temperature ratings, which determine the maximum operating temperature of the conductor. High temperature rated insulation allows conductors to operate at higher ampacities. The NEC specifies the allowable ampacities for various insulation types, such as THHN, THWN, and XHHW. Fourthly, ambient temperature affects ampacity. The ampacity of a conductor is typically based on a specific ambient temperature, such as 30 degrees Celsius or 86 degrees Fahrenheit. If the actual ambient temperature exceeds this value, the ampacity of the conductor must be derated to account for the increased heat. Fifthly, the number of current-carrying conductors matters. When multiple current-carrying conductors are bundled together, the heat generated by each conductor can raise the overall temperature within the enclosure, reducing the ability of the conductors to dissipate heat. As a result, the ampacity of each conductor must be derated to account for this increased ambient temperature. The NEC provides tables and formulas for calculating these derating factors based on the number of current-carrying conductors. Applying the correction factors found in the NEC involves several steps. Firstly, determine the base ampacity of the conductor. This value is typically found in NEC Table 310.16, which provides ampacity ratings for different conductor sizes, materials, and insulation types based on an ambient temperature of 30 degrees Celsius. Secondly, determine the ambient temperature correction factor. If the actual ambient temperature exceeds 30 degrees Celsius, a correction factor must be applied to the base ampacity. The NEC provides tables that list these correction factors for different insulation types and ambient temperatures. Thirdly, determine the number of current-carrying conductors. Count the total number of current-carrying conductors in the raceway, cable, or enclosure. Remember to include all phase conductors and any neutral conductors that carry significant current. Fourthly, determine the adjustment factor for the number of conductors. Use NEC Table 310.15 B3 to find the adjustment factor that corresponds to the number of current-carrying conductors. This factor is expressed as a percentage. Fifthly, calculate the adjusted ampacity. Multiply the base ampacity by the ambient temperature correction factor and the adjustment factor for the number of conductors. The resulting value is the adjusted ampacity of the conductor. Choosing the correct conductor size requires careful consideration of several factors. Firstly, calculate the load current. Determine the maximum current that the conductor will be required to carry. This can be calculated using the formula current equals power divided by voltage for single-phase circuits, or current equals power divided by voltage times the square root of 3 for three-phase circuits. Secondly, apply any applicable derating factors. Adjust the calculated load current to account for ambient temperature and the number of current-carrying conductors. Thirdly, select a conductor with an ampacity greater than or equal to the adjusted load current. Use NEC Table 310.16 to select a conductor size that has an ampacity rating that meets or exceeds the adjusted load current. Fourthly, consider voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. Fifthly, comply with local codes and regulations. Local electrical codes and regulations may impose additional requirements for conductor sizing. Be sure to consult with a qualified electrician or electrical engineer to ensure compliance with all applicable codes. An open delta system, also known as a V-phase system, is a type of three-phase electrical power system that uses only 2 transformers instead of the 3 transformers used in a standard delta system. Open delta systems are typically used in situations where the load requirements are relatively small or where the cost of installing a full delta system is prohibitive. An open delta system consists of two single-phase transformers connected in a V configuration. The primary windings of the transformers are connected to the three-phase power source, while the secondary windings are connected to the load. The open delta system provides three-phase power at a reduced capacity compared to a full delta system. The capacity of an open delta system is typically about 57.7% of the capacity of a full delta system using the same size transformers. Open delta systems have several advantages. Firstly, they are less expensive to install than full delta systems because they require only two transformers instead of three. Secondly, they are more flexible than full delta systems because they can be easily converted to a full delta system by adding a third transformer. Thirdly, they are more efficient than single-phase systems for powering three-phase loads. Open delta systems also have some disadvantages. Firstly, they have a reduced capacity compared to full delta systems. Secondly, they are more susceptible to voltage imbalances than full delta systems. Thirdly, they require careful consideration of the grounding and overcurrent protection. Open delta systems are commonly used in a variety of applications. Firstly, they are used in rural areas to provide three-phase power to farms and other remote locations. Secondly, they are used in small commercial buildings to power air conditioning systems, pumps, and other three-phase equipment. Thirdly, they are used in industrial facilities to power small motors and other loads that do not require the full capacity of a full delta system. When designing an open delta system, it is important to carefully consider the load requirements, the voltage drop, and the grounding and overcurrent protection. It is also important to consult with a qualified electrician or electrical engineer to ensure that the system is installed and operated safely and in compliance with all applicable codes and regulations. Nonlinear loads are electrical loads that draw current in a non-sinusoidal manner. These loads create harmonic currents, which can cause a variety of problems in electrical systems, including overheating of conductors and transformers, voltage distortion, and interference with sensitive electronic equipment. Examples of nonlinear loads include computers, electronic ballasts for fluorescent lighting, variable frequency drives, and other electronic devices that use switching power supplies. These devices draw current in short pulses, which creates harmonic currents that flow back into the electrical system. Harmonic currents are multiples of the fundamental frequency of the electrical system, which is typically 60 Hz. For example, the third harmonic is 180 Hz, the fifth harmonic is 300 Hz, and so on. These harmonic currents can cause a variety of problems in electrical systems. Firstly, they can cause overheating of conductors and transformers. Harmonic currents increase the root mean square, or RMS, current in the electrical system, which can cause conductors and transformers to overheat. This can lead to insulation failure, equipment damage, and even fires. Secondly, they can cause voltage distortion. Harmonic currents can distort the voltage waveform in the electrical system, which can cause equipment to malfunction or operate inefficiently. Voltage distortion can also interfere with sensitive electronic equipment. Thirdly, they can cause interference with sensitive electronic equipment. Harmonic currents can generate electromagnetic interference, or ME, which can interfere with the operation of sensitive electronic equipment such as computers, medical devices, and communication equipment. There are several ways to mitigate the effects of harmonic currents in electrical systems. Firstly, use harmonic filters. Harmonic filters are devices that are designed to block or reduce harmonic currents. They are typically installed at the point of connection of nonlinear loads. Secondly, use harmonic mitigating transformers. Harmonic mitigating transformers are transformers that are designed to reduce the amount of harmonic current that flows back into the electrical system. Thirdly, increase the size of conductors and transformers. Increasing the size of conductors and transformers can help to reduce the effects of overheating caused by harmonic currents. Fourthly, use separate neutral conductors. In three-phase systems, it is often beneficial to use separate neutral conductors for circuits that serve nonlinear loads. This can help to reduce the amount of harmonic current that flows in the neutral conductor. Fifthly, comply with IEEE Standard 519. IEEE Standard 519 is a standard that provides recommendations for limiting harmonic distortion in electrical systems. This standard can be used to help ensure the harmonic levels are within acceptable limits.